අයිබෝවන් සුබ සන්ධ්‍යාවක් ප්‍රාර්ථනා කර සිටිනවා ඔබ සියලු දෙනාටම. ස්ථාපාටි 2025 තාරකා විද්‍යා වැඩමුළුවේ දෙවන දිනයත් සමගින් ඔබ අද මෙලෙසින් එක්ව සිටින්නේ. හිමායා.
The stars are the landmarks of the universe. They are the eyes of the heavens, observing and knowing all. A very good evening to you all. Welcome back to the second evening of Exploring the Unknown. In 2004, the Astronomical Societies of Mahamaya Girls College and Down the Boys College launched Star Party, a sky-gazing workshop and competition designed to inspire and engaging participants in the wonders of the night sky. Today, we're excited to kick off the second workshop brought to you in collaboration with Star Party 2025.
අද දින මෙම දේශනයට සම්පත් දායකත්වය ලබා තිබෙන පැමිණ සිටින නාසා ආයතනයේ විද්‍යාඥ ආචාර්ය හෙන්රි රූප් මහතා ගෞරවයෙන් පිළිගන්නා අතරම එතුමන්ට ආරාධනා කර සිටිනවා මෙතනට සිය දේශනය ආරම්භ කිරීමට.
We are incredibly honored to have with us today Dr. Henry Throop, a program scientist at NASA. He will be sharing his expert insights into NASA's New Horizon missions, taking us on a journey to the Kuiper Belt and beyond. We're thrilled to have him, and we're sure his lecture will be both fascinating and inspiring. Please join me in welcoming Dr. Henry Throop.
Hello. Thank you. Can you hear me?
Yes.
Okay, thank you. It's such a pleasure to be here. Let me share my slides here. Let's. Okay, do you see my screen there?
Yes, sir.
Okay, thank you. So I will commence with the lecture then. So my name is Henry Throop. I'm an astronomer at NASA headquarters in Washington, D.C. And I'm so excited to be talking with you here today. I actually live in Sri Lanka. I've been in Sri Lanka for 3 years. I've had the pleasure of coming over to Ananda College, and I'm so excited to be able to deliver this virtual lecture to you today. So I'm going to be talking about the New Horizons mission, which is a spacecraft which NASA sent to Pluto and beyond in our solar system. And so for context, here we have a picture of a galaxy. So this is someone else's galaxy, not ours, but our star is just one of these 100 billion stars in the galaxy. And if you zoom into our star, you see the sun at the center. And then around it, you have the 4 other planets made of rock, which are Mercury, Venus, Earth, and Mars. Outside of that, and we call these the rocky planets because they're basically like the same as the Earth. Outside of that, we have Jupiter, and then we have Saturn, and then we have Uranus, and then we have Neptune. And these we call the gas giant planets because they're basically made of gas like hydrogen and helium, and gravity still keeps them all stuck together. And then out beyond that, we have the icy planets. We call the first one here Pluto, and then we have many, many other Kuiper Belt objects in the outer solar system. Pluto is the largest of these, but we have thousands and thousands of these. And the main reason for the difference here is when you're close to the sun, it's very hot. And when you get further and further from the sun, it gets colder and colder. And so that's why we have the ice at the outer edge where ice is stable. But then if you come in, the ice melts or the ice turns to gas. And so you don't have the ice on the rocky planets or so much of the gas giant planets. But as you go out, then you have ice because the ice stays cold when you're far from the sun. So sometimes you go outside at night, just like you could right now. You go outside and you can see Mercury, you can see Venus, you can see Saturn, Jupiter, the moon, of course, Earth. Many of the naked eye planets are all visible at the same time. And so you can see all these here. It's hard to see Uranus, Neptune, Pluto, or the asteroids because they're too faint. But other than that, you can see pretty much all of the bodies. And people for thousands of years have been able to see these bodies in the solar system, the planets. So in 1874, Urbain Le Verrier was looking at the position of Uranus, and he was studying Uranus, and he was plotting its position, and he knew it was going around the sun in kind of an oval position. And he was plotting its position, moving through the sky, and he saw that it was deviating a little bit from what he thought it should be. And he plotted it out, and he said, well, I think Uranus is being pulled around by something else. I think there's something else whose gravity is influencing Uranus, and I think it's another planet. It's called Neptune, and it's going to be right up there. So he predicted Neptune, and he looked up there with the telescope and found it essentially the next day. So it's one of the most remarkable discoveries in astronomy, where he predicted Neptune's existence and then found it very shortly thereafter. So in 1905, Percival Lowell was an astronomer at the Lowell Observatory in Arizona in the US. And he was looking at Neptune, and he said, I don't think that Neptune is in the right place. I think Neptune is being pulled around by the gravity of something else as well. And so he went up and with his telescope, and he started looking around for something pulling around Neptune, and he called it Planet X. So he looked and he looked and he looked, and he didn't find it. He didn't find it, and then he died. And so, but before he died, he hired someone to help him. And this guy he hired was a guy named Clyde Tombaugh. So he was hired to search for Lowell Observatory, and here's what he did. So he used a little trick. He used this telescope here, and this is a 13-inch telescope, and he took pictures of the sky. Now, if you look up in the sky, you can name the constellations. We can name like the Orion constellation, and the deal with Orion, the stars stay together in one formation, right? That's what we call the constellation. And so you can take a picture of Orion one night and the next night and the next night and 10 years later, and it's all pretty much the same. 100 years later, the stars in Orion, they stay in the same place in the sky. They rotate every night, but they stay fixed together in the same place. So Clyde Tombaugh did this, and he used a little trick. This trick is that the stars are in their fixed position, but anything which moves is not a star. And so he was looking at things that moved, which must be planets or asteroids or comets or something new that he'd never discovered before. And so he took pictures of the sky with the stars here one night, and then he came back and did it the next night. And if you look really closely, you can actually see one thing that moves here from one night to the next. I'll circle it here. There it is circled. Here it is here. Okay, there it is. So this is actually the very first discovery image of Pluto. Now, that was in 1930. We didn't know very much about Pluto at the time. We knew that Pluto was, it took 250 years to go around because we saw it move through a portion of the sky, and that meant it takes 250 years to move through the rest of the sky. And we could see that it was moving, it was pretty faint, so it's pretty far away. It's moving slowly, it's far away, that means it's cold. We could guess at how big it was, but we couldn't see any, the pictures didn't show any details on the surface or any moons or anything like that. So that's what we knew for when it was first discovered. A little bit later in 1976, about 40 years later, we found a moon going around it. You can see this little lump on one side of Pluto, and the moon, then the lump a couple of days later ends up on the other side. Now, it's kind of hard to see this lump. This picture's kind of grainy. That's because it's taken with a very old telescope using photographic film. But what he did find is that every 3 days, this lump would move from one side of Pluto to the other. And 3 days later, it would come back up here like that. And so this was actually Pluto's moon. And there's a moon called Charon. There you have the first discovery image of Charon. And every 6 days, it orbited Pluto. So that was in 1978. We found Pluto and Charon. Now, this picture here is a picture kind of what Pluto and Charon look like with each other. This is with a Hubble Space Telescope, where you can see Pluto right here and Charon right up here. Now, that's a much better telescope than the telescope that was used to detect Pluto and Charon, or detect Charon in the first place. But they're resolved here. But you can see that Pluto just looks like a ball there. You can't see any markings on its surface. You can't see any craters or valleys or anything like that. It's just Pluto there. And that's because even with the Hubble Space Telescope, this is the best image that you can take of Pluto. So we used the Hubble Space Telescope. We looked for more moons going around Pluto. In 2006, we discovered a couple more, one named Nix, one called Hydra. In 2011, we found one more called Kerberos. And then I was part of the team, which in 2012 found one more called Styx going around Pluto. And Pluto's really bright there. Pluto's where those crosses are, but the moons are much fainter. So we've kind of scaled it so you can see the moons, but not Pluto there. So you could put everything that you know about Pluto that you can detect from the Earth on one slide here. We can measure its size. We can measure its density from how fast gravity makes the system pull the moons around. We know it has an orbital period of 248 years. We can tell a little bit about what it's made of. Its surface composition is a lot of ice, things which are really cold. We can tell it has a little bit of atmosphere, 5 moons, but we can't really see anything on the surface. And so any more exploration requires close-up visit. So you want to get a close-up visit, you can do 2 things to increase your resolution. One, you can just build a telescope on the ground. You can build like a bigger and bigger telescope, right? Okay, so you can build a huge telescope on the ground. On the other hand, you can just take a small telescope and fly it to Pluto. That's the other way to explore something in the solar system. And that's what NASA does. So we mostly take small telescopes to explore the solar system. At least what we do is we take a small telescope and we fly it out to the planet, and we use it that way. So this is our spacecraft. So this is the New Horizons spacecraft. This is a $700 million spacecraft. It's funded by NASA, built by 2 groups. One's called the Applied Physics Lab, APL, and one's called SWRI, the Southwest Research Institute. It's about the size of a car or a piano. It's a robot, so there's no passengers on here. It's no people, because people can't travel in space in a box like this. It's very small. People would be complaining. And what it did, it flew past Pluto, it took pictures, and then it sent them back over its radio link. And it's going to keep flying. It doesn't land. It doesn't orbit Pluto. It doesn't take samples of Pluto. It doesn't bring them back. Its job is just to go past Pluto, take pictures, and then send them back. And if you look at it, the components of it, we've got some cameras, we've got a radio, we've got a battery on it. And so this is basically the same thing as something you all have with you. It's basically the same as your mobile. You got this nice iPhone 16 Pro here, and it's got a camera, and it's got a battery, and it's got a radio on it, and the same things as our spacecraft does. Now we have a bigger battery than the iPhone does. We have a better camera and a bigger radio, but it's the same basic idea. You're basically going to click a photo and send it back over the radio link, and that's what our spacecraft does. Now, here's the instruments on our spacecraft. Down at the bottom, we have a couple of telescopes, like the one called LORRI. On the right, LORRI is our black and white camera. And so it's a telescope about this big across. It takes black and white images. On the right band, we have one called Ralph over there. Ralph is a color camera. Then we have one called Alice. Alice is a UV spectrometer. So it's looking at the composition of the atmosphere, the atoms in the atmosphere. Ralph, looking at the infrared, looks at the molecules that make up the surface of Pluto. And we have a couple of instruments that are looking for the solar wind. And then we have one on the bottom, which is pretty cool. It's called the SDC, the Student Dust Counter. And this is actually built by students at the University of Colorado in the US. And these students, they built this thing. It's basically a big piece of piezoelectric film. And what this does, it acts kind of like a drum. And so whenever it gets hit by a dust sensor, it puts out a voltage. And this voltage can be detected and allows us to use the spacecraft itself as a dust detector. You might not be that interested in dust, but it turns out if you get hit by dust particles, that can tell you about the history and the environment of where you are in space. And so because dust is kind of leftover debris from making the planets, and so it can tell you about the history of the solar system by listening to these tiny, tiny dust particles that hit the spacecraft. So we were selected by NASA in 2001 to send our spacecraft to Pluto. There was a competition, and the group I was with had the proposal that was selected to win this competition. So took about 4 years to build the spacecraft. And so 2002, 3, 4, and 5, we were building the spacecraft and testing it. And then by January 2006, it was ready to launch the spacecraft. And so we went out here. And if we could have the annotation turned off, someone is drawing on the screen. Could we please have the annotation turned off so people cannot draw on the screen? Thank you. So here we are in 2002. We have the spacecraft. We're building it at the Johns Hopkins University Applied Physics Lab outside of Washington, D.C. And here we have one of the instruments. This is the infrared camera, which we are insulating and covering up here for to secure it. Here we have people assembling the wires on the spacecraft to connect the wiring harness for the antenna. There's many, many meters of wires. This looks like the doctors with their baby in the lab as they're building it. And spacecraft rotates when it's in space. And so we need to balance it, make sure it's properly balanced before it goes into space on the rocket. And so in 2005, we're finishing this up. So we have a large team of scientists and engineers who are working together on the spacecraft. So we have close to, there's 200 people on our core team and probably thousands more who worked on the spacecraft. At the center there in the black shirt, that's Dr. Alan Stern. He's the principal investigator, the head of the mission. I'm in the way back there, and we have lots and lots of other team members who are scientists and engineers and writers and documenters and IT people and managers and accountants, because it takes everybody to work on this mission. So when I started, I was based in Boulder, Colorado. And so Vishnu, I think, looks like is writing on the screen. So could you please clear that from the screen? Thank you. So we have the spacecraft, which is being built in Colorado and then taken down to Texas. Parts of it came from the East Coast. It was all assembled on the East Coast and then launched from Cape Canaveral in Florida. In 2006, by January 2006, we were ready to assemble this at the Cape Canaveral in Florida and get it ready for launch. So here we have it on the rocket. So you have the nose cone up top there, and then you have the rocket with its booster rockets on the side there. And the rocket is essentially a flying fuel tank. Most of the weight of the rocket is just fuel. In fact, the spacecraft is just a couple hundred kilograms. The rocket is a couple 100,000 kilograms, so thousands of times more mass is in the rocket than in the spacecraft. And so it gives out about 2 million pounds of thrust. The rocket only burns for about 40 minutes and then disconnects. And so it's kind of like throwing a ball. You throw the ball in the right direction, and if you toss it right, it's going to hit the target. And same thing with a spacecraft. You throw it in the right direction, and as long as you've aimed it properly, given it enough momentum, then it's going to get to the right location. Thank you for clearing the screen. So the main fuel tank that we have here is contained with liquid oxygen and other things. I think Suraj is drawing on the screen now. Please, Suraj, clear the screen. Thank you. If we could please disable the annotation on the screen, because we don't want people drawing on the screen. Thank you. So here we are at the spacecraft as the rocket is rolling out to the launch pad in Cape Canaveral, Florida. And here we have the team who's assembled to watch it go off. Now you can see the large building on the right. That's not the launch pad. The launch pad is the tiny, tiny one in the middle there, far, far away. It's about 10 kilometers from us for safety. And you can see thousands of people here who are assembled to watch the launch. And we watch it, and it goes off, and it's so exciting here. So I can't tell you how exciting it is. This is the mission which we've been working on for 5 years, and it finally goes off into the sky. So here we have some of the scientists and engineers who are working on the mission as we're watching it go in through the clouds into space. This is one of the geologists on the mission, one of our colleagues, the artist on the mission. And I'm going to play a short video of the launch here. Now, can you hear the audio coming from the video there?
No, sir.
Okay, I'll tell you what's happening then. So there's this is where at T-minus 45 seconds, we're waiting for the launch to happen here. And so you can see the water vapor, or the vapor that's coming off of the spacecraft. These are the booster rockets. The booster rockets give it a little bit of extra power. You can see the tower on the right there is actually a lightning rod, because we don't want lightning to be hitting the spacecraft. So we're doing the final safety checks here. We're at T-minus 18, 17, 15, 14, 13, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long journey to visit the planet Pluto and then beyond. So it's accelerating into the sky above the waters of Florida here. T plus 15 seconds. Everything continues to look good as the Atlas V vehicle continues to climb away from Florida's east coast. The 5 solid rocket strap-ons are burning just fine, sending the New Horizons spacecraft on its way to the very edge of our solar system. So we're following it here with telescopes on the ground, and also we have some very fast airplanes which are chasing it now. This thing is already going faster than the speed of sound, even T plus 40 seconds into flight. What's going to happen here is the solid rocket, all the engines are burning together right now. You can see the solid rocket boosters and the liquid engine are all working. The spacecraft is just in that tiny compartment right up front here. We're 1 minute into flight, and we're going eastward above Florida and over the ocean. Now, this spacecraft, this rocket, as I said, is only going to burn for about 40 minutes. But some of the parts of the rocket, in fact, the solid rocket boosters, which you can see on the side there, they've almost burned out completely. They've almost used all their fuel. Once they've used all their fuel, there's actually no need to take them along. And so we're going to remove them. We're going to pop them off. They're going to jettison off. SRB-4 is burned out. All chamber bursts are responding. So SRB, that means the solid rocket boosters. So if the solid rocket boosters have burned all their fuel, then we're going to get rid of them. So you'll see them pop off here in a minute. We have the main RD-180 engine, which is the liquid engine, which is throttling up. So there's the booster rockets popping off. They're going to go back down to the Earth. And so this continued for about 40 minutes of burning. They were just about 2 minutes in until the spacecraft was on its way to go to Pluto. So if you go down Marine Drive at night, no traffic around there, you have a really fast car, maybe you can get up to 250 kph if you're racing there. At that speed, it might take you about a year to get to the moon. The moon is about 250,000 kilometers away. Apollo 11 took 4 days to get up to the moon. With our spacecraft, how long did it take to get to the moon? 9 hours, because we're going so fast. We're going 10 times faster than Apollo. Now, how did we go 10 times faster than Apollo? That's just the laws of physics. That's pretty easy because we had a really low mass, and so we got a high velocity. So it's just conservation of energy. Low mass, high velocity. That meant we could get to the moon quickly. The reason why we had a low mass is we built our spacecraft intentionally to be very small. That's why we didn't put any people on it. We didn't put a rover on it. We didn't put anything on it that we didn't have to. In fact, there's almost no moving parts at all. There's almost nothing on the spacecraft except for the fuel that needs to get there, the cameras that needs to get there, the power that needs to use, and the radios and electronics and the cameras that it's going to be used there. Okay, so we launched in January 2006. A year later, we passed Jupiter. And after that, we're just going through space. So 2008, 9, 10, 11, 12, 13, 14, and finally in 2015, we would cross the orbit of Pluto. So here's a map of what we're doing. I see a hand raised. We'll take questions at the end. So please put your hand down and we'll have plenty of time for questions at the end. Thanks. So we passed Jupiter 1 year into flight. We took some great pictures of Jupiter, which I'll show you. And then the next thing we passed really was Pluto. And we were programmed to meet up with Pluto at where the yellow orbit and the white orbit intersect each other there, where it says Pluto, July 2015. And then you can see we can keep on going outward into the Kuiper Belt. So here we are at Jupiter in a year after launch. This is the highest resolution global image of Jupiter, which has ever been seen. You can see its red spot there and the belts and bands of its atmosphere. You can see here Jupiter's moon are Jupiter's rings. Jupiter has rings just like all of the gas giant planets have rings. The rings are like kind of broken up moons. They're made of dust. They're made of small particles like that. And they're often at the same place as these moons are. So moons and rings and dust, they all are kind of at the same place. This is the series that I like the best. This is the little video that we took of a volcano going off on Io. Io is a moon of Jupiter. And all these things that you can see on the surface there are volcanoes. But what you can see is the plume going off in real time on the top of Jupiter. Just amazing to really see this in real time. We knew there were volcanoes on Pluto or on Io, but we'd never actually seen them go off like this. So we have 9 years to get out to Pluto. What are we doing during that time? Are we just sitting around taking a nap? Nope, we're working hard. And the reason why we're working hard is we know that we have just one chance to go past Pluto. And so every when we go past Pluto, if we miss it, we can't turn around. We can't turn the spacecraft around and fly backwards. And so we just have one opportunity, and everything has to be optimized to get the most science and the best images out of that flyby of Pluto. So what I was involved with here, my role during the mission, a couple of things. Before launch, I was working on the infrared spectrometer, working to calibrate that. During cruise, meaning after launch, when the spacecraft is on its way out there, I worked on a lot of the tools used to plan the observations and search for dust. And then when we're at Pluto, I spent a lot of time looking for new satellites and looking for new rings at Pluto itself. So when we were selected to launch, we were just going to go past Pluto and its moon Charon, because that's all we knew about Pluto and Charon, kind of a double planet system. Now, right about this, just before we launched, we found 2 new moons named Nix and Hydra. And then after launch, using the Hubble Space Telescope, we found 2 more moons called Kerberos and Styx. So instead of having 1 moon, we actually have 5 moons now by this point, 5 moons. And so that's great. On the one hand, that's really exciting because we have 5 times much science we can do, right? It's really exciting to have all these extra things to look at. But there's a big problem too. So here's our image with the Hubble Space Telescope of the system. And I showed you earlier this image of Jupiter's rings. Jupiter's rings, I said, wherever you have moons, you have dust and you have rings. Now that would be kind of like the worst case scenario is if you go to Pluto and maybe there's rings and dust and moons going around. Where there's more moons, there's rings and dust at Pluto as well. And so that could be super dangerous. So Riham, please don't draw on the screen. So a dust particle, which is this tiny, can end the mission. And that's because the dust particle is going at 50,000 kilometers per hour. And at that speed, then any piece of dust can be catastrophic for the mission. Now, we can't see an individual millimeter-sized dust grain because a dust grain just 1 millimeter across can be dangerous for the spacecraft. We can't see the spacecraft, or we can't see the dust grains. What we can do is look for dust grains using Hubble and with New Horizons. We can't look for individual dust grains, but we can look for clouds of dust grains. And so we did this. We searched around. After several years of work, we concluded that space around Pluto was not dusty, and we could fly New Horizons past it like we planned to. Okay, so by early 2015, could we have the screen cleared, please? There's a couple of people who've drawn on the screen, unfortunately. Could we have that cleared? So by 2015, New Horizons had traveled about 5.5 billion kilometers, and at this point, it was time to turn on our cameras and look at Pluto. Before that, Hubble was able to see Pluto more clearly than we were. Thank you for clearing the screen. But by this point, we're getting close enough that we wanted to turn on our cameras. So here we are. So here's the first color image that we took of Pluto. You can see Pluto and Charon right there. And then soon after that, every day, we get more and more better and better images. So here we are, April 15th, a couple of months before encounter, and we can see here we are again. You can see Pluto and Charon orbiting each other around their common center of mass. And then here we are in June, and our closest encounter is set for July 15th. So about 2 weeks out from the closest encounter right now. So we can see every day the images get bigger and bigger. Uh-oh, and then they stopped. Okay, so July 4th, we were uploading our final command sequence to the spacecraft, and we're sending it over a giant network of radios. It's called the Deep Space Network, and we're sending it up to Pluto, and we're looking for the spacecraft to acknowledge us, and we couldn't find it. The spacecraft just vanished. And so we looked around, we called up the radio dish, and they're like, hey, is your radio dish working? And they were like, yep, it's working. We just can't find the spacecraft. And so we hunted around, and about 4 hours later, we found it, and it was transmitting on a backup frequency, and it was kind of confused. It didn't know what had happened. And so we listened to it tell us, and it said that it had rebooted and it didn't know what had gone wrong, but it had some sort of problem on the spacecraft. Now, this is July 4th. We're supposed to get this. We have 10 days until we're supposed to get to Pluto, and suddenly the spacecraft is broken on us. And so sometimes, if you're out at the mall, if you're out with your friends, you might get separated from them, right? And so you might, you text your friends like, hey man, where are you? And your friend will, she'll text you back, and she'll be like, hey, I'm over here, like, oh, I'm here, and so forth. And so you'll talk back and forth a couple of times and figure things out. So we could do the same thing with our spacecraft, but we didn't want to do it too many times. And that's because every time you talk to the spacecraft, it takes 4 hours for light to travel out to the spacecraft, light on radio. And then the spacecraft has to think about it. Then it spends 4 hours to send the signal back. And so it's 8 hours round trip. And so every time you do that 8 hours, 8 hours, 8 hours round trip, time is clicking away. And so we did this a couple of times. And we figured out the spacecraft was in safe mode. And we figured out there was actually a problem with the software on the spacecraft. And thanks to our mission operations manager, Alice Bowman, and the group of engineers that she ran, we figured out what was wrong. So they found the spacecraft, they woke it up, they figured out what caused it to disappear, which was a problem with the software, it was a bug. And so they rewrote the system software and they tested it, and they reprogrammed the spacecraft from 6 billion kilometers away. And 2 days later, we were back on track. So this is the closest we came to losing the spacecraft. It was very close. It was very hairy. And thanks to the ability of the engineers on this mission, then the images resumed coming back down. So here we are, July 8th, 2015, July 9th, July 12th. We're 2 days out from our closest approach. So should we, I'll tell you what's going to happen here, the closest approach. So at 3 a.m., we're set to receive the highest resolution global image of Pluto. The spacecraft can only do one thing at a time. So the spacecraft can either take pictures or it can send those pictures back to us. It can't do both things. And each picture, so the spacecraft is so far away that each picture, when it sends down, is going to take many hours to send it down. It's kind of like if you go out with your friends and you're if you take 1,000 pictures, then it might take you, a day to send those 1,000 pictures back. But then if you just have 1 bar of service, it's going to take you even longer. So we're much less than 1 bar of service with our radios. Very, very slow. And so the spacecraft is programmed just to take pictures and not send them back. It's going to send us back 1 picture the whole day, which is that highest resolution global image of Pluto. And it's going to spend the whole day observing Pluto. 7:50 in the morning, it's close to Pluto, as it does. It's about 3,000 kilometers above the surface. And then we have one time where we tell the spacecraft, okay, turn back to Earth, transmit a brief phone home message to Earth. Then the Earth is going to hear you, tell the astronomers that it's working okay, and then go back to observing some more. Okay, so here we are. So that's what's going to happen. Here we are. We're at the hotel. There's a couple hundred scientists and engineers who are at the hotel room, waiting to go out to the lab in the morning. Here we are. We're assembled at the lab. This is 6 o'clock in the morning. We have all the scientists and all the engineers who are waiting here. Do you want to see the first image of the surface of Pluto? Show it to you. Wow. It makes me happy to see this every time because it's so cool. So this is our first global full resolution image of Pluto. So we have what you see here is this looks unlike anything else in the solar system. It's got these big dark areas. It's got these big bright areas. It's got the kind of shiny stuff up top. It's got some craters on it, but not that many craters on it. And it's got this big heart over here because we love Pluto and Pluto loves us too. So here we have some of the scientists on the mission. These are the geologists. They're really excited to be seeing the geology up close here for the first time. The whole team here as we're looking at this image, which is so exciting. And geologists, on Earth, geologists just love to walk up mountains and down valleys and into craters and so forth. And the team was doing the same thing with the images of Pluto. that were up there. Our first one single image of Pluto had the geologists really doing the same geology in real time on the surface of Pluto. So we spent the day looking at that one image. And then we're waiting. There's one other thing that's going to happen today, which I told you, which is that at 8 o'clock in the evening, we were going to hear back from the spacecraft. And so here we are, we're assembled, we're waiting, we're trying to hear back from the spacecraft to see what's happening. And here we are, this is you can see Alice Bowman there on the phone. She's talking with the radio antenna group to see what she can hear from them. And as she hears from them, then we see that the spacecraft is healthy and has gone through the Pluto system. And so everybody gets super excited to hear the great news, the success of the spacecraft. So this is one of the geologists on the mission, some of the friends and family of the mission. And what's remarkable here is after 9.5 years and 6 billion kilometers, we arrived 1 minute early. Now, why did we get there 1 minute early? How could we be so accurate about this? It's because the laws of physics work. We know how gravity works. We know how our rockets work. We know how F equals ma works. We know how all this stuff works in the solar system. And so that lets us predict the motions of the planets and of our spacecraft so accurately. Okay, so here we have Pluto. So we have this nice global image of Pluto. And you can look at, if you look at the surface of Pluto, it looks very different than the surface of anything else. On the left here, we have the surface of the moon, and the moon has craters all over it. These craters are not volcanoes. These craters are caused by asteroids or comets hitting the surface of the moon. And in fact, the moon has so many craters on it that essentially, whenever it's what we call saturated with crater, whenever you put one crater down, it's going to cover up another crater, which is already there. So it's got this surface which is billions of years old. Pluto, you can see a couple of craters here. Pluto's the one on the right. You can see a couple of craters here, but not that many. Like there's a handful that you can see there. But so what it means is that it looks like the surface has been like repainted, redone, smoothed out pretty recently. It's not billions of years old, but maybe 500,000 years old. But we know that Pluto was sort of formed at the same time because all the planets were formed at the same time. But for some reason, it looks like Pluto is much newer than the rest of the planets. They didn't really know why. And we still don't really know why, but it looks like something is active on Pluto to recover the surface, to do some geology on the surface to get rid of the old craters. Now we can take that same image, we can stretch it in Photoshop a little bit. And so here we're looking at the same thing, but we've just stretched the colors, made them more extreme. And so what you can see is that, kind of like the dark red areas, that's probably organic molecules. It's kind of like a haze or a soot that's been put down on Pluto somehow. There's kind of those yellowish areas up top is like carbon dioxide ice. The bluish areas are like nitrogen ice. And then the area in the heart has like some whitish ice and some pinkish ice. And so all of these things are the different colors of the different ices that are on Pluto. And in fact, in the room that we're all in right now, the Earth's atmosphere, we have ices. We have ices in the Earth's atmosphere. And if you were to take ice that you're breathing, take the atmosphere that we're all breathing right now and take it down to the temperature at Pluto, which is only about 20 degrees, 30 degrees above absolute zero, all of the atmosphere that we're looking at right now and breathing would actually turn to snow and ice. So in your room, you would have a little layer, a couple of millimeters thick from the atmosphere in the room right now. So we can zoom into Pluto a little bit. Here we are this is in the middle of the heart. You can see the kind of smooth areas. They kind of look like, kind of like polygons, little different shapes in the ground there. And what this is probably is just it's kind of like making a pudding on the stove that it's kind of boils and turns over and stuff like that. Now, Pluto is not boiling, but it's a very cold and very slow moving, but it's the same sort of thing. There's heat inside of Pluto, which is trying to escape. And as that heat tries to escape, it actually turns over the surface of the ice on Pluto. So this is kind of like in the Himalaya, where you have ice. Ice is a solid, but if you have a glacier, the solid can slowly move, and so the glacier can flow down the mountain. The same thing, the same way that these glaciers of nitrogen ice are moving on Pluto. Here we have what looks to be a big hole on the surface of Pluto. We can see mountains. You can see the height of the mountains just by looking at the length of their shadows, just like you've measured your height by measuring the length of your shadow. You can do the same thing on Pluto here up at the top. You see those shadows. Here we have some mountains of water ice, which are poking through the nitrogen ice. And you see a couple of impact craters, but not very many. So again, it looks like a brand new, fresh surface. Here's Pluto's moon called Charon. On Charon, it looks like there's maybe some icebergs, kind of like icebergs on the top and maybe an ocean in the bottom where the icebergs have kind of broken off into this ocean. So it used to maybe be all liquid down the bottom there. Or there's a crack maybe from thermal expansion or contraction on the surface of Pluto. So you can also, we took images of all of the moons, 5 moons, Charon, Nix, Styx, Kerberos, and Hydra. And that's driving it. That's all the moons orbiting Pluto. Now we didn't go close to them, but we did see enough of them to see them quite well. And so we're making maps of all the features and mountains and craters and so forth on the surface of Pluto. You can see the maps named for people and mythologies and explorers all around the whole world. It's one of my favorite pictures here. This is the Norgay Mountains, the mountains here on Pluto, and as we're leaving the Pluto system, because we were at Pluto for just about one day. So we took all these pictures in one day. So we're looking backward, and you can really see the height of the mountains and the shadows of the mountains. And you can see also in the atmosphere, you can see all the different layers of the atmosphere on this coming off of Pluto. So it tells you about the history of Pluto's atmosphere. One scan here, we're just looking across that white region, the heart region on Pluto, and you can see all the different shapes and colors in the craters, all the structure inside the crater, what look like cat scratches there. Then the terrain is getting a little bit bumpier. You see more canyons in here. See more mountains in there and little chasms between them. And then suddenly it changes to look like a coastline. Now it's not a coastline because this is still frozen nitrogen. Looks like we have sand dunes here that are blown around by the wind. And then you have some things like sailboats that are poking up in here, and all these other structures in the surface of Pluto. Now, what I predicted at Pluto was that Pluto was going to be cold and dead. Going to have lots of craters there. Everything I predicted was wrong. I mean, it's dead in the sense that. So thank you, Shamed, for removing your text from the image. What we thought would be there wasn't really what was there. We expected to see lots of craters, or I expected to see lots of craters. But we found instead this is a very active surface. There's lots of geology happening, very recently on the surface of Pluto. Even though Pluto's old, it's actually very active. So my predictions were wrong. That's okay. Whenever you make predictions, you learn much more when you find something which is wrong rather than being right. You get a lot more points for being wrong than being right. Okay, so we went to Pluto in 2015, and it took about 2 years to transmit all of the data back to Pluto, back from Pluto to the Earth. And as you can see, as we pass Pluto, and then we're going to this green box here. That green box is a region of the Kuiper Belt. And what should we do now? So we looked at the map, we looked at where we were, and we're like, well, let's look for a Kuiper Belt object out here. And so we found one. We used the Hubble Space Telescope, and we found one right there. And its name was Arrokoth. It was discovered by Hubble in 2014, just before we got to Pluto. And you can see how it's moving there. 1, 2, 3, 4, 5. That's Arrokoth moving across the sky. And so pretty easy. We just wanted to go over to it and take some pictures of it. Now, it's easy to say that, but it's actually pretty hard to actually go to it. And that's because Arrokoth was so small that we don't know its exact size, its shape, or its position. And that makes planning our flyby of it really hard. Because Arrokoth, this Kuiper Belt object, it's 1 million times smaller than Pluto. It's 10,000 times fainter than Pluto. It's 2 billion kilometers further away than Pluto. We don't know its size. We don't know its position, its orbit, or its brightness. And in order to take pictures of it, what we had to do was target our cameras at it precisely with the right exposure in the center of our frame while flying in the dark at 50,000 kph. Now, the most simple thing, like, okay, find its position. Okay, couldn't we just do that with a Hubble Space Telescope? You can do that for easy if you want to find the position of Saturn or Jupiter. You just point the Hubble at it and you can measure its position. But for something like Arakoth, it's so tiny that you can't actually measure its position very well. So, we have these images and we zoom, this is a Hubble image, right? And we zoom it in and we zoom it in a little bit more and we zoom it in more. And like these pixels just get fuzzier and fuzzier, right? So you can't zoom this thing in anymore. With Hubble even, you have not nearly the resolution, 100 times less resolution than you need to actually measure the position of this thing precisely. There's another tricky way you can do this. So the best way to measure something is with Hubble, but if you can't use Hubble, what you can use instead is this trick, which is kind of like a solar eclipse. If you're looking at this at the sun, sometimes the moon will go in front of it, like once every 20 years in Sri Lanka, 50 years, something like that, like it did in Jaffna about 15 years ago. And when the sun gets blocked out like that, you know exactly where the moon is, and you can measure the moon's position precisely because it's right in front of the sun. Same thing happens with stars. So there's some stars, and you can watch the star, and occasionally that star will disappear. If that star disappears, there's an asteroid or a comet or a planet, something like that, in front of it. So we could actually predict. We knew that Arakoth was about to go in front of a couple of stars, and so we set up to make these detections. Now these are really hard detections. We had to use some largish telescopes. We had to go to the right place in the world. So just like a solar eclipse, you have to use the right telescope. And you have to be in the right place at the right time to observe a solar eclipse. So what we did was we bought a bunch of telescopes, we rented a bunch of trucks, and we took these down to South Africa, which was the right place and the right time to make this observation. So you can see our telescopes there. We set up our telescopes to try to watch this star get disappeared by the Kuiper Belt object moving in front of it. So just like the path of the solar eclipse, this shows you the path of where that star is disappearing because the Kuiper Belt object's moving in front of it. And so we had a group set up in South Africa. We had a group set up in Argentina. And we had months and months of planning for this 3-second observation. Here is where my group was. We were set up in a ostrich farm in South Africa. And we didn't actually successfully measure it there. We missed it. But we had lots of other teams that were set up. They missed it also because we were all looking in slightly the wrong position. But that helped us refine where we were looking. So the next time we looked at it from some different telescopes, another position, then different telescopes the next time. And finally, we started to nail this thing. And so we went for a bunch of different eclipses, a bunch of different locations. And finally, we got to figure out its position. Once we did this, we knew its position, and then we could target our spacecraft to fly past it. So here it is. So here's a picture of Arakoth as we're getting close to it. And every day, just like approaching Pluto, every day we're getting closer and closer to Arakoth. So there it is there it is, there it is. This is our network, our operations center outside of Washington, D.C. You can see all of us are in this building here in the center. And Arakoth, we're getting closer and closer to it every day. Now with Pluto, it was getting bigger and bigger every day. With Arakoth, it's still so tiny because remember, this thing is 1,000,000 times smaller than Pluto. So it's not until you're right on top of it that you can actually see it in detail. So even the day before we got there, we couldn't see it yet. And so we were supposed to get there on New Year's Eve, January 1st, 2019. We were celebrating because most people on the Earth were celebrating right at midnight. We were celebrating at 12:33 a.m. because that's when our closest approach to Arakoth was. And so here we are just after midnight as we're celebrating that our spacecraft had gone past it yet. Now, we didn't receive any images yet, but we received word from the spacecraft that it had successfully gone past the Arakoth system after a journey of 6 billion kilometers and 12 years. And here we are. Here we are looking at the very first image of Arakoth coming down. It looks kind of like this snowman. It's got like 2 balls here. I'll show you a better picture of it. Here's a better picture of it. Here's a better shape of it. And we did pretty well predicting its shape and its position not using Hubble, not using James Webb, but just using these small telescopes that we set up in Africa and South America. So really exciting, really emotional to actually have this successful flyby. And then our images started to come down. And so you can see our first images were a little bit rough, but then as we waited for the higher resolution images to be sent, the images got better and better and better. And finally, now we have this nice color image where we can actually see what's going on with Arakoth. You can have debates about whether Pluto is a planet or not. With Arrokoth, you cannot have a debate about it. It's not a planet. This is an ancient planetesimal. It's the oldest thing we've ever seen in the whole solar system. It's been untouched for 4.5 billion years. Nothing's ever seen it. Nothing's ever touched it. This is what the planets were made of. It's 30 kilometers across. Comes from a region of the solar system that we've never visited, and it's never visited us. So you can see it looks like two bodies here. There's a big one, there's a small one. Looks like they kind of slowly impacted each other like this, not violently, because there's no big craters there. In fact, there's just a couple of tiny craters there. So it's probably a pretty empty region in the Kuiper Belt, and things are going at really low speeds in the Kuiper Belt. The bottom half there looks like it's made up of the merger of other smaller bodies, kind of like a bread roll down the bottom half there. And then in order to make Pluto, what happened is you took like 1,000,000 of these things, and these are planetesimals, and you had 1,000,000 of these things, which all came together to make Pluto. So that's our flyby of Pluto and Arrokoth. Now our spacecraft is still going. Right now, we're still searching for another flyby target. We started in 2022. We're still searching for this other flyby target right now. We haven't found anything else to fly past yet, but you can bet that if we find one, we will try to target our spacecraft to go there. In another couple of years, we'll leave the Kuiper Belt. Eventually, we're going to leave the solar system. Now, it's going to take us another 50,000 years to leave the solar system because the solar system is big. And then we'll get to the next nearby star in about another 5 lakh years. We'll get to the next nearby star. Now, our spacecraft isn't going to last that long. Our batteries and fuel are going to only last for maybe a decade or so more. But the spacecraft is going to continue on, even with no fuel, even with no batteries, out into the interstellar region. So here's our team. Thank you so much for traveling with us to Pluto, to Arrokoth, and beyond. There's our website. You can follow the updates from the mission as we continue to explore outward in the solar system. Thanks so much.
If anyone have questions, it's time for them.
And you can put your questions in the chat, or you can raise your hand and we can do questions that way. Either way is fine. So the question is, who took images of the satellite? So the pictures of New Horizons itself were taken. Some of those were taken on the ground. If there's there was one picture of New Horizons flying past Jupiter, and that was just an artist's picture of it. That was everything else is a real picture of the spacecraft. Okay. The question is opinions on a unified theory for quantum gravity. So I know that quantum gravity is a area of a lot of interest in the world. I don't study. That's an area of cosmology, which has to do with the origin of the universe, not of the solar system, and it's not something I know very much about. So I would search for the Wikipedia article on quantum gravity. Akash says, "Thank you so much. Valuable and clear, amazing lecture." Okay, Vihanga says, why are black and white cameras used? And the thing is here, we had 2 cameras. One was the color camera, which was low resolution, but color. And then we also had a black and white camera, which was high resolution. You can always build a black and white camera will always be higher resolution than a color camera because you can make smaller pixels with it. So we used the 2 different cameras. And then for the color images, we merged the color and the black and white.
Excuse me, doctor.
Yes, just 1 second. Yes, please go ahead.
My question is, first, previously you said New Horizons was the fastest spacecraft ever launched, and you said the reason for that was low mass and high velocity. Can you please explain me how we can achieve that low mass and velocity using theoretical methods like rocket equations or others?
Yeah. So the rocket equation, you're exactly right there. So the rocket equation is what determines the velocity of a rocket if you have a certain amount of energy, a certain amount of fuel that goes into it. And so basically, you can calculate the speed of New Horizons if you know the mass of the spacecraft, which is about 500 kilograms. And if you know the mass of the fuel, which is about 500,000 kilograms, you put those in, and you put some other factors in there, and that would give you the eventual speed of the spacecraft, which is about 50,000 kph. I'm going to read a couple of questions that have come in directly to me here. Is there an ocean under the glaciers of Pluto? We don't know. Originally, we thought no, because Pluto is so far away, so small, so cold, there can't be any ocean there. But now it seems like some people are thinking about like maybe there could be an ocean. Maybe it's not quite water, but maybe it's like a slush, kind of like a snowy ice ball in there that has some liquid in it beneath the surface. Question is Arrokoth the oldest thing in the solar system? No, it's not the oldest thing in the solar system, but it is the oldest thing that we have flown past. So we've never seen anything this old before. There are many, many other objects like Arrokoth out there, millions more like Arrokoth, which are just as old, but this is the one that we have gone to and seen up close. How old is it? As a question of Pluto, and everything in the solar system was made about 4.5 billion years ago. So we think the solar system, everything was made at basically the same time. And the reason we think that is we can see other solar systems form, and you basically have a cloud of gas and dust, and then all the dust sort of sticks together and makes the planets. And it takes a little bit of time, but it's pretty quick once you have all the dust there. And so we think that all the planets were made within a couple 100 million years of each other. And so they're all essentially at the same time. Maybe Pluto was formed a little bit later than the Earth, but not a billion years later than the Earth. Question from Kavit, will there be another expedition to Pluto? The answer is yes, there will be, but we don't have one planned right now. I only say yes, not because we're planning on one, but because the solar system has so many fascinating areas in it, and I suspect that down the road, eventually, maybe decades down the road, we'll have another spacecraft. There's so much more to explore there. There's so much, such a fascinating area. Pluto and the rest of the solar system will no doubt be visited by spacecraft from the US and from India and from Japan, and perhaps even from Sri Lanka, as Sri Lanka begins to participate in the global space exploration as well. Okay, question is, will a rover be sent up to Pluto? Perhaps eventually a rover will be set up. Right now, we don't know exactly where the rover would go. So what we would want to do is orbit Pluto first, take some high-resolution maps of the surface, and then figure out where the most interesting and most safe place to send a rover is. Its question is Planet X Pluto? Yes, same thing. On Planet 9, Planet X, it's all kind of the different terms for the same thing. So that's what we mean by that. Okay, question from Rasandi is, what's the true origin of Pluto's highly eccentric orbit, and why does it have such an unusual tilt compared to the other planets? And the answer is that in the outer solar system, the tilt of, most things are tilted. In the inner solar system, it's easier to have a flat orbit. So Mercury and Venus and the Earth have a very flat orbit. It's not tilted at all. But as you go further out, it becomes easier and easier to be tilted. And so as you go out to the Kuiper belt, it's pretty tilted. And then if you go out to the Oort cloud, they're kind of like all over the place. And that's because the gravity isn't as strong out there. They're not moving as quickly. There's not as many other things on flat orbits to pull them into flat orbits. And so there's just, and they're sort of, they haven't been going around as many times. And so there's not as much force to pull them into a flat orbit. So is it a question from Roshini, is it possible to have water in Pluto? Yes, Pluto definitely has water on it. Now the water is probably frozen and not liquid. So there's probably not life that we're looking for there, because life that we know of requires liquid water. It's very cold at Pluto too. So chemistry moves slowly, but there probably is, there is certainly water at Pluto. It's just frozen in ice. Question from Vidat is, how much did this entire operation cost? The New Horizons mission was about $700 million. So it's paid for by NASA. NASA is the US government space agency. It's the largest space agency in the world and the first space agency in the world. And so NASA is not trying to make money. NASA's job is to spend money. and explore the universe for the benefit of everybody. And so, in fact, when I say everybody, what I mean is you here can download all of the data, all of the images, all of the measurements from Pluto, and you can use them. Anybody from Sri Lanka can go to NASA's website and download all the data. Anybody from India can. Anybody from Australia, anybody around the world can use all of the data which NASA has taken in your own research. All right, question is here. I've heard about the DART mission. There's a new target for New Horizons, or DART. Could you confirm whether it's just Arrokoth or something from DART is a mission to the asteroid belt? So DART was an unrelated mission. That was a mission to an asteroid called Dimorphos in the asteroid belt. And so it was actually we had an asteroid here, and we slammed the spacecraft intentionally into the asteroid to try to move it a little bit, to understand how we can move asteroids if the asteroid is headed toward the Earth. So that was a test mission. That impact happened about 4 years ago. So that's what the DART mission was. We don't have another target for the DART mission because the DART spacecraft was impacted and then destroyed in that impact. And we don't right now have a new target for the New Horizons spacecraft. If we find one, then we will try to divert the spacecraft if we have enough fuel to do so. So by 2007, here's a question from Ozma. By 2007, New Horizons flew past Jupiter. By 2015, it reached Pluto. And you said New Horizons reached 1 minute early. Was the gravity of Jupiter used to increase its velocity? Yes. So we use these gravitational flybys, the slingshot maneuver, to try to speed up Jupiter, or speed up New Horizons as it goes past Jupiter. We've used that slingshot maneuver during many of the other flybys in the solar system, like the Voyager spacecraft used that all the time as it flew past Jupiter, Saturn, Uranus, and Neptune. Question from Mevni is Pluto the only dwarf planet you've explored close up so far? What about Haumea, Makemake, Eris, and Ceres? Ceres and Vesta, we've actually explored. Those are asteroids. They're in the asteroid belt, and there's a mission called Dawn, DAWN, and it's explored 2 of those asteroids called Ceres and Vesta, which you could call dwarf planets. Haumea, Makemake, Eris have not been explored yet, and they are fascinating worlds. I hope that we are able to go up to them sometime, and we just need to. It's just a matter of having so many targets, and we have to. We don't have a spacecraft to go to every single one because we need to optimize the science here. Question from Nirosha: do you have a mission to find a new planet that living beings can live? So as far as right now, the best place for planets for us to live on is definitely the Earth. Anywhere else is either too hot or too cold. Nowhere else that we know of has an atmosphere, has water, has food, things like that. So the best place to live is right where we are right now on Earth. So Dahamia says, how much time will it take for a spacecraft to go out of our solar system? Going at the speed that New Horizons is going, it will take about 50,000 years to go out of the solar system, and about 500,000 years to go to the next stellar system, which in this case would be like Proxima Centauri. Question from Rasandi: what causes sudden warming and active geology on Pluto as observed by the New Horizons mission? Your guess is as good as mine. No one knows. So we don't really know the whole story of Pluto's interior. If you're interested in this, you should study this, and you could. There's many people who join NASA. If you want to join NASA, if anyone else wants to join NASA, you should. How you can do this is study. Go to uni here in Sri Lanka. Study physics, study biology, study chemistry, study something like that. Be at the top of your class, and then apply. Number 2, apply to postgraduate programs abroad. So you can apply to postgraduate programs in the UK, in Germany, in the US, in Australia, places like this. And there's great postgraduate programs. If you come to the US, you may get your education paid for by NASA to work with NASA to explore many of these questions. And once you have at a postgraduate program, you can earn a PhD and an MSc. And once you've done that, then you can be an astronomer and work with NASA and other groups around the world. And that's what I've done. That's what many of my colleagues have done. And many of my colleagues are from Sri Lanka. There's many famous, well-known and active Sri Lankan astronomers and scientists and engineers. Question from Covey, is the slingshot occurring in a planetary alignment powerful? Yes, that's because gravity is really powerful when you have a really big planet. Gravity is a weak force. You can't really feel gravity between two people, right? But you really do feel gravity between like a person and the Earth, or between a spacecraft and a planet. That's when you really feel gravity. So gravity can be really strong if you're close to a planet. So that's why this slingshot maneuver works. Question from Chanuti. Is Arrokoth the most interesting thing about Pluto so far? So I think the most interesting thing about Pluto so far is just how active the geology is, how young the surface is, how it was really different than what we predicted. So Emoja asks, "Sir, will Pluto go from dwarf planet to a true planet?" The answer is no. Something doesn't change from a dwarf planet to a true planet. It's just a question of how big it is, and there's really no difference between a dwarf planet and a planet. It's just that a planet is like this big and a dwarf planet is like this big, and this is like like a rock, and this is like a piece of dust. And so it's just a question of how big it is. Like, what's the difference between a peak and a mountain, or a mountain and a hill? Maybe a mountain is 1,000 meters and a hill is 100 meters. But where do you draw the line exactly between a hill, between a mountain and a hill? That's the same thing with how big a planet is. How many subplanets to Pluto? So Pluto has 5 moons: Charon, Nix, Hydra, Cerberus, and Styx. So 5 submoons. Rasandi asks, what's the source of Pluto's hazy atmosphere? Why is it so variable? That's a great question. So it is really variable. We don't really know why, but Pluto goes through very strong seasons. So parts of Pluto you don't see for dozens and dozens of years, because Pluto is turned in such a way. It has to do with its orbit and its tilt. And so Pluto is turned in such a way so that we actually can't see it for a long time. And so that probably caused a lot of its atmosphere to sort of freeze out on one side of it. And then, many years later, that atmosphere comes out. And so that caused its seasons to be a little bit more extreme than the seasons on the Earth. Okay, does Pluto have subplanets? Yes, the answer is yes. Pluto has 5 moons, which are subplanets. Okay. Let's see. Yonal says, my brother worked in NASA. Congratulations. I have not met your brother, but I know there's so many great Sri Lankans who are working at NASA. Question is, how does NASA take pictures of the Big Bang and things like that, which was created over 13.8 billion years ago? So we've not taken pictures of the Big Bang itself, because all the it's already happened, and we can't actually physically go back in time. But what we can do is we can use things like the James Webb Space Telescope, which is essentially it can look in wavelengths, looks in red, in the infrared, and we're looking in the infrared. We're looking at things which happened, which are a long way away from us. And if they're a long way away from us, that means they happened a long time ago. And so that's stuff which happened in the beginning of the universe. Not at the Big Bang itself, but they happened more for the beginning than we are now. Okay, so question is, Doctor, are there any living organisms in Pluto? We don't know of any. I think it's probably very cold for having life on Pluto, but we could be surprised as well. But this was not a mission to look for life. Nirosh asks, how's the heart in Pluto made? Is there a special reason? It's just probably a kind of random. There might have been an impact crater where an asteroid or comet hit Pluto right there. It made that kind of heart-shaped area. It's just a coincidence that it's shaped like a heart instead of shaped like a circle. Most craters are shaped like a circle. Perhaps this was 2 craters that were right next to each other. They overlapped, and that's why it looks like a heart. So Dahamya asks, why is Pluto not a planet? Not a planet because some people call it a planet, some people call it not a planet. It's just a question of size. Pluto's the smallest of the planets, and it's sort of the largest of the Kuiper Belt, or smallest of the planets, but you could call it either way, really. Okay, question is, let's see, have there been space rocks to be verified from Pluto or the Kuiper Belt? And can we use them to study the complexity of Pluto's atmosphere? So we don't have any space rocks which have actually come from Pluto or the Kuiper Belt. We do have space rocks which have come from different places. Like there's lots of meteorites which we've detected. Right near here, I've got a meteorite that came from the asteroid belt. Here I've got a metallic meteorite that came from the asteroid belt as well. Now these are very different than Pluto because they're made of metal, not made of ice. If something comes from the Kuiper belt, it's going to be made mostly of ice, and so it's going to kind of break apart. Um, this is actually a piece of Mars right here. So this is caused when there was an impact on Mars that knocked some rocks off of Mars. They orbited throughout the inner solar system, and then this thing landed in Africa, millions of years later, and was picked up. So it was a piece of Mars that got pushed off, and it's very unlikely. It's very difficult to get something from Pluto all the way down to Earth. I won't say it hasn't happened, but we certainly have never discovered one that we know about. And then a follow up to that, if there has been space rocks from Pluto, could we use them to study the complexity of Pluto's atmosphere? The answer is yes, absolutely. So this Mars rock, you can actually, it has some of these Mars rocks have Martian atmosphere, which is trapped inside of them. And so by very carefully extracting that atmosphere, you can actually study the atmosphere that was on Mars 3 billion years ago. Question is, what is the name of those submoons from Diwani? The answer is you can look those up on Wikipedia, but I'll tell you right now. The big one is called Charon, and then Nix and Hydra, and then Styx and Kerberos. Question from Netuli, is Mars suitable for living beings? That means, is there suitable temperature, congenial atmosphere, and enough water? Nope. Mars is a terrible place to be. It's not the right temperature. It's too cold. There's not a good atmosphere. It's 100 times less atmosphere than we need. And there's no water. There's very, very little water. So Mars is a terrible place to live. If we go to Mars, we will die. There's interest in going to Mars eventually with humans. But you need to take along your own atmosphere. You need to take along your own water. You need to take along your own food. And so you cannot just go there as a regular person and survive on the surface of Mars, just like the surface of the moon. Okay, so question is how to go to the satellite on what speed does the satellite go in space? And this is going about 50,000 kilometers per hour. Question is the simulation theory true? What's my idea? Simulation theory is the idea that the universe just might be a simulation of the universe. And it's hard to prove that to be wrong or prove it to be false. So you can read about the different philosophies of that online, but I don't really have an opinion on it myself. Okay, Vihanga says, does Charon affect the movement of Pluto? Yes, indeed. So Charon and Pluto affect their movement affects each other, and so you can tell from the movie that I showed that Pluto and Charon kind of go around each other, and Pluto orbits Charon, and Charon also orbits Pluto, and so this causes they orbit around each other's common center of mass. So one pulls the other around, and the other pulls the other around as well. Okay. Can I explain about the white hole theory? White holes are very dense regions, kind of like black holes. I'm not an expert in white holes. So in order to learn about white holes, what your best bet, the Wikipedia, I was just reading the Wikipedia page on white holes recently. You should go there because they know a lot more than I do about white holes. Is there a planet called Planet X? Planet X is Pluto. That's it. Now, there's another idea. People have now come up with another planet, which might be beyond Pluto. So, 100 years ago, when people were looking for Pluto, they called it Planet X or Planet 9. Now, there's actually a group which thinks there might be another planet out beyond Pluto. And this is a planet which maybe it would be a giant Jupiter, far, far beyond Pluto, beyond anything else, 10 times further out or 20 times further out. And we don't know whether it exists yet. It's very hard to detect with telescopes. It's very, it's moving too slowly and it's too dark to really see very easily at all. Maybe it's there, maybe it's not. There's some evidence from gravity that there might be something out there, but maybe yes, maybe no. Okay, can I explain about black holes? Black holes are just very dense. So basically, anything in the solar system has an escape velocity from it. And so the bigger something is, if you want to jump away from it, its gravity is going to hold you down. Like, this little meteorite has a bit of gravity on it. So if you're standing on the meteorite, you have to jump to leave its surface. And then something that's bigger and bigger has a stronger and stronger gravity. Something which is more and more massive or more and more dense has a bigger and bigger gravity. And so if you take something and you make it super, super dense and massive, it's got so big a gravity that you can't jump from it no matter how fast you're going. In fact, even the fastest thing in the universe, which is light, cannot escape from it. So that's a black hole. Now we've seen black holes. You can't see the black hole because it's black, like space. So it doesn't look like anything. But you can see the black hole by the motion of other things around the black hole, which are being influenced. They're influenced by its gravity. So in what speed does the ISS travel? The ISS, the International Space Station. In fact, it just passed over Sri Lanka last week. I was looking outside to see it go over Colombo. It was cloudy, unfortunately, so we couldn't see it, but we were all outside with my family and kids. We were watching the ISS come over. So it goes, it's in what's called low Earth orbit. And so it goes, what is it, 15 kilometers per second, something like that. It takes about 90 minutes for it to go around the whole Earth. Question is, how do astronauts go into the International Space Station? Astronauts go up on rockets, either rockets from some go from NASA on SpaceX, some go from Kazakhstan, some go from Boeing, and so those astronauts, they go up there, they stay in the space station for a while, and they come back down. The space station is not very far away. The space station is only 300 kilometers away. So if you've been to like Chennai, India, that's further away than the space station is. The space station is very close, 300 kilometers. Okay, sir, do you have some more things like that you showed before, like parts of asteroids? So here's another one. This is pretty cool. This is actually a meteorite here. Also, now this is a meteorite that you can actually, yeah, that's cool. So you can actually see through it. So it has some crystals in it. This is something called a palisite, which is a kind of meteorite. And so these are crystals of something called olivine. And so this is a special kind of meteorite, came from one particular asteroid. So it has metallic and these olivine crystals in it. And then this one is pretty cool because it's got these crystals of metal in it. You can see them right there. So this is actually from the oldest meteorite which has ever been found. I think it's something like 4 billion years old. And you can see this is the crust of it. This is where it was burned up in the atmosphere and falling to Earth. And then that's the interior of it. This one here was this is one that I bought in Morocco a couple years ago, and the deal with all these meteorites, they're all found kind of the same way. Is that if you go to Morocco, for instance, or Saudi Arabia, or Algeria, and you're walking around, I mean they're mostly desert, right? So it's sand, and it's like you're walking, and it's sand, 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 sand. But then you come across a big black rock in the middle of the sand, and there's no volcanoes around. There's nowhere there where this big black rock would come from. So where did the big black rock come from? Came from space. Same thing happens in Antarctica. If you walk around Antarctica, it's all ice, right? But then if you're walking across the ice, you see a big black rock. That rock came from space. It's a meteorite. So every year we have groups of people who go down to Antarctica and look for meteorites. We have people that go to Africa and look for meteorites. And so this particular meteorite is just someone who lived in Morocco. They found it and they sold it to a store, and I bought it there. I didn't collect any of these myself. I bought them all. Okay, question is there a subsurface ocean in Europa? And the answer is yes. So Europa is this moon of Jupiter. NASA has the spacecraft, and it's going up there right now. We launched it last year, October 15th, and it's on its way. It's going to take about 5 more years to get to Europa. And Europa is fascinating because it has this ocean going underneath the whole surface. It's kind of like going to the North Pole on the Earth. North Pole, it's frozen. It's got ice on the top. But if you go below the ice, then there's a big ocean there, right? And the ocean has, whales and sharks and coral and whatever in it. we don't know what's in the ocean in Europa, but maybe it's the same thing. Maybe it has coral and sharks and whales and bacteria in the ocean in Europa as well. Maybe it's the same as the Earth. Maybe it's completely different than the Earth. Maybe it has nothing at all. Maybe it's dead. We don't know, but we want to explore it. So that's why we have the Europa Clipper mission, which is going up there. And the European Space Agency has a mission called the JUICE mission, which is the Jupiter Icy Moons Explorer. And so you can read about both these on Wikipedia. They have great articles. If you just search for Europa Clipper or you search for JUICE spacecraft, then you can learn about them there. Okay. Question is, how did Pluto's moons, especially Charon, form, and what role did they play in shaping Pluto's geology and history? That's a great question. So we think that we're not totally sure, but we think that here's the best idea is that you might have had, you had Pluto here, and then you might have had an impact into Pluto, which formed Charon going around it. And then the small moons might have been asteroids, which are captured. Like the asteroids are Kuiper belt objects, things like that, which just came too close to Pluto, and then they're sort of drawn into orbit around it. But we honestly don't really know. They might be, maybe they were all captured. Maybe they were, multiple of them were created by impacts. We don't really know. So these are things that you can study. If you are interested in studying these, you can learn about orbital dynamics, you can learn about gravity, and you can study it in uni here, and then you can apply for postgraduate studies and continue your work, and maybe you can answer that question yourself. Okay, Ashwaf asks, in the past, were there volcanoes on the moon? Yes, there were. So the moon does not have active volcanism right now on it. It's pretty dead. But in the past, there were definitely volcanoes on it. There's evidence of lots of lava, lots of moonquakes, lots of shakes and shifts and stuff like that in the moon's geology. The moon has a lot of geology going on to it. Question, can I explain about wormholes, please? Is there any wormholes observed near our galaxy? And I don't know much about wormholes, but wormholes we've never detected a wormhole. We've never seen one. They might exist in theory. So it's possible the laws of physics allow a wormhole. And that would be like if you go here and then suddenly you come out here. Maybe they exist, maybe not. It's an idea that some theoretical physicists have been talking about, but we don't really know whether they exist or not. So right now it's just an idea. How many black holes in the universe, asks Gihan. The answer is many. There's 100 billion stars in every galaxy, and there's 100 billion galaxies in the universe. And so each galaxy probably has many, many black holes. And so that would be hundreds of billions of black holes throughout the galaxy. Not every star will turn into a black hole. Large groups of stars may end up with a black hole. The center of the galaxy, center of the Milky Way, has a black hole at it. But not every star. Okay, question is, I saw a video that said the Milky Way and Andromeda are going to collapse in the future. Is that true? Yes. So we've got the Milky Way galaxy over here, which is where we are. It looks like a spiral. And then we have the Andromeda galaxy, which you can see at night. It also looks like a spiral. And they are, in fact, coming close to each other. They're going to collide with each other. Now, that's not really a problem. It will not cause any influence on the Earth. You will see the stars in the sky change because they will have new positions after that. But it will not be an explosion. It will not be a crash. It will not really change life on Earth here. Also, it will be in maybe 1 billion years. So unless you live for 1 billion years, you will probably not see this happen. But it is true that the Milky Way and Andromeda are coming closer to each other. Okay, question is there any use of traveling to Ganymede? The reason why we do all of this is to explore, and because we're curious, we want to do science. So there's no use to doing any of this, but we are humans, and we are curious, and we want to explore the universe. Question is, what galaxy is next to the Milky Way? And that is the Andromeda galaxy. You can see the Andromeda galaxy at nighttime if it's dark. If you go down to Tangal or to Trinco, you could see the Milky Way galaxy from there. From not the Milky Way, the Andromeda Galaxy. It's very hard to see the Andromeda Galaxy from Colombo, but sometimes if it's very dark and you get on the outside of Colombo and there's no clouds, then it could be. Okay, question. How might the tidal forces between Pluto and Charon be linked to the surface activity seen on both bodies? Could they be affecting each other's internal structures? Yeah, it's possible. It's possible. It's probably so that question, that's a good question, Rizani. So on Jupiter, Io and Jupiter kind of their gravity links them, and that's why Jupiter's or Io is being pushed like this, and that causes the volcanoes because you're transferring a lot of energy through their tidal forces. And that's because Jupiter is really, really big, and Io is much, much smaller, and it's kind of caught in a resonance between Jupiter and the other moons as well. Now, in Pluto, there's probably not as much going on because the gravity is much weaker because Pluto is so much smaller than Jupiter, and the gravity of the other bodies is really small compared with the other moons at Jupiter. So any resonances and any heat being dissipated is much, much less. But maybe there's something. Maybe there's something a little bit. Yeah. Question is, can we live on Pluto? If we went, is there any risk to that? And it is too cold to live on Pluto. You'd have to take your own water and food and oxygen, and it would be about 250 degrees negative Celsius. So unless you had all that with you, you would die very quickly. Okay, so Kalana asks, so what do I think about the lowest point of gravity on Earth? Lowest point of gravity is indeed Sri Lanka. It's very interesting. It's the Earth is spinning, so any place on the Earth that's near the equator has low gravity. But then also the rocks underneath Sri Lanka are different than there may be lower density rocks or a thinner layer of rocks than in other places on Earth. And so, in fact, the gravity from Sri Lanka is a little bit less. And here's how much less it is than the North Pole. On the Earth in Sri Lanka, I weigh about 200 pounds. But if I were to go up to the North Pole, I would weigh about 199 pounds. So it's about 0.5% difference from 200 pounds to 199 pounds. And so that's why the weight is a little bit less in Sri Lanka. So I'm sorry, 199 on Sri Lanka, 200 pounds on the North Pole. Just due to the rotation of the Earth. That's most of the effect, is the rotation of the Earth. And then a tiny bit of that effect is that the density of the rocks in the ocean underneath Sri Lanka are just less dense than anywhere else on Earth. It doesn't really mean that it's the best place to launch rockets from because there's no rocket. You'd have to ship the rockets all the way from where they're made to Sri Lanka. It's not a very big difference for launching a rocket, but it is measurable. What's the planet in the solar system with the highest density? I think that's probably Mercury. You would have to look that up though, but I think it's probably Mercury. Does Pluto have tidal locking with its subplanets? That's a great question. When we first went to Pluto, we thought they were not locked, and then we thought they were locked, and the argument has gone back and forth on those. I actually forget whether they're tidally locked now or not, but you can look them up and research what the latest status of that is. Let's see. Let's take about 3 more questions. So one question, why Jupiter has a high gravity? Jupiter has a lot of gravity because there's a lot of gas there. And so probably what happened is that Jupiter just had a lot of gas there and then it formed to a big planet. And then when it formed to like a halfway big planet, by that point, it starts stealing the gravity from everything else around it. So if there's one planet that's a winner, it's going to start stealing gravity from everything else and get bigger and bigger and bigger, and nothing can stop it. Okay, so how do the gravitational forces between Pluto and Charon affect Pluto's surface and atmosphere? Probably not very much. The gravitational forces are not very strong between Pluto and Charon, but one thing which is strong is that I showed you the on Charon. Actually, I don't think I showed you, but on Charon it has a kind of a red layer on top of Charon, and that's probably related to the atmosphere, like haze, which is produced in the atmosphere, and there's a deep red layer which is on Pluto as well. And so probably what's happening is that we're actually producing haze particles, which are like smog kind of, in the atmosphere on Pluto, and they're being sent through space due to Charon's gravity over to Charon and actually being deposited on the surface of Charon, all these particles in from the atmosphere. Even though Charon doesn't have much of an atmosphere itself, it's actually grabbing it from Pluto. Okay, so how does the gravitation, and from Gihan, what part of a comet points most directly away from the sun? That would be the tail of the comet, points away from the sun. And how dense is the atmosphere on Pluto? The atmosphere on Pluto is about 1 lakh times less dense than the atmosphere on the Earth. So 100,000 times less. There's so many questions, and those are great. All of these are great questions. You've learned so much, and you've paid attention so much. And I have to answer this one. So if the asteroid coming toward the Earth, what will happen? I've heard there's a 2% chance of it hitting the Earth. And in fact, there's something which, so NASA is very interested in finding asteroids which are headed toward the Earth, because we are in a position where we can influence them now, like we did with the DART mission. And so the Earth gets hit by comets and asteroids all the time. Every day, the Earth gets hit by about 40 tons of asteroids and comets and shooting stars. All of this stuff, all of these are essentially asteroids and meteorites that hit the Earth from space. And so what we do, we've detected recently with a NASA telescope an asteroid about 50 meters across, something like that, that has a 98% chance of not hitting the Earth, but a 2% chance of hitting the Earth in something like 10 years. I forget the exact time. And so if it does hit the Earth, this is something which could damage a small region. It would impact a small region of the Earth. We see this happen all the time. We see this happen like about 100 years ago. There was a similar sized body that hit in a part of Russia, and this is a body called a comet called the Tunguska impactor, and you can look it up on Wikipedia. There's a good article about it, Tunguska. There was another one, a little bit smaller, that hit Russia also by coincidence about 15 years ago, and it was called the Chelyabinsk impactor. And this one here that we're looking at now has is of similar size, and so we've been hit by things like this, millions of times in the past, right? But we definitely want to monitor this and see if it's the sort of thing that we want to do anything. We're with the DART mission, we were able to, as a test, move the orbit of an asteroid, and this one here is sort of a follow-up to that. And so it'll be very interesting to follow these observations. Again, 98% chance it's not going to hit the Earth at all. 2% chance that it may impact the Earth, like these other ones which have hit in the last 100 years. That's what we have time for. So I'm going to stop the questions now. I wish we could go on for hours and hours more, but that's what we have time for. Thank you.
We'd like to extend our sincere gratitude for your insightful lecture, Dr. Throop. Your passion for space has inspired us all. And thank you all for joining with us today. And make sure that your calendar is marked for tomorrow's lecture too. Thank you.
Bye-bye.